What's up, everybody? Hope you all doing well today. We have 10 conservation of energy review problems we're going to do. I'll put a link to a PDF of all these problems so that you can try them first, and I'll also try to link to each chapter so you can skip around if you need to. Alright, without further ado, let's start with question number 1. In this problem, we have a crate that's just being pushed, and we're pushing with a force. We're going to calculate some work here. Okay, so remember, work is force parallel to distance, and they don't specify that it's horizontal. Like, it could be at an angle, I guess, but if it was, they would specify that. So we're just going to assume that it's already parallel. So it's just going to simply be 20 newtons of force times 10 meters. That gives us 200 joules of work. Alright, letter B says now how much power. So remember, power, that's essentially like the change in energy over time, or in this case, the thing that's changing energy is us doing work. So we could write that as work over time. So we're simply just going to go 200 joules, and the time was what, 2 seconds? So that gives us 100 joules per second, or 100 watts. Letter C says, what's the velocity after pushing? So in this thing, you want to think about, well, my energy initial equals energy final. That's conservation of energy. So we'd say, well, I'm doing work, right? That's where the energy is coming from. And that's turning into kinetic energy. I'm pushing it. So all that work's going to turn into kinetic energy. So if we're saying, well, there's 200 joules of work, that means there must be 200 joules of kinetic energy. And from there, we can just simply calculate our velocity, right? So we'll go 1/2. The mass was 4 times v squared. Okay, this cancels. That's 2. That means 100 equals v squared, which means v is going to be simply 10 meters per second. Alright, let's move on. Letter D. Alright, so our crate's going to keep moving, right? We're going to move it up a ramp. So here's our crate. It's moving along at a speed of 10 meters per second. And then it's going to head up a ramp. How high is it going to go? Well, that's what we're looking for, right? So we know that as it's rising, it's going to be changing energy type. So down here, we'd say we have all kinetic energy. And up here, all that kinetic is going to turn into potential energy. So when we do our initial equals final, see, this is letter D, right? Initial equals final, well, the initial energy we already know, right? We calculated that earlier. That was 200 joules. And we know our final energy is turning into gravitational potential energy. So we're going to try to figure out how high is it going to go before it stops. So we'll just use our equation mgh. Remember, you do have to define your reference level. In this problem, it's pretty easy. We'll just define the reference level to be the bottom. That's where h is equal to 0. So that makes the problem pretty straightforward. So this is going to be 4. This is going to be little g, 9.8. And we're going to solve for the height. So go ahead and do that. I'm getting 5.1 meters. That's going to be the maximum height. Now this question is saying, well, imagine this. Imagine that it doesn't go 5 meters. It only goes 3 meters, right? So there's going to be some friction that's going to kind of take away some energy, right? Some of that energy is going to turn into heat energy, so it's not going to go quite as high. So to solve this, just go ahead and pop this up a bit. To solve this, we're just going to, again, just use our same concept here, conservation of energy. E initial equals E final. Again, our E initial, we already know, right? Once you solve it, you can just kind of stick with that, 200 joules. So we're going to have mgh, we're going to have some ug here, right? It still goes up, but we're also going to have some energy that, we'll just call this energy lost. That's kind of whatever energy is left over. So we'll go mgh plus, we'll just call that E lost. We'll go ahead and sub this in. So mgh is 4 times 9.8 times 3, right? Because it didn't go the full 5 meters, or 5.1. So I'm going to do this one out just a little bit further. So we have 200 joules equals, for this one we get 117.6. That's how much potential energy we have, right? So we started with 200, we're left with 117. That means we lost some of that energy, right? Or specifically, we didn't really lose it, it just turned into heat energy, right, through this process of friction. So subtract those two, I'm getting an energy loss of 82.4 joules. All right, let's move on to question number 2. All right, we have a roller coaster problem. So in this one, we're going to start up here at point A. Our roller coaster is going to be heading down. It starts with a velocity. It's going to be heading down to point B. It's going to be moving up to point C. And then we're going to hit the brakes and eventually stop at point D. So we're going to solve several things in this problem. Just go step by step. So letter A is asking how much kinetic energy is at the top. So to find the kinetic energy at the top, that's just a simple 1/2 mv squared calculation. So the mass was 2,000 and the speed at the top was 5 meters per second. Don't forget to square that out. That's a common mistake that students tend to make. So I'm getting a kinetic energy of 25,000 joules. So letter B is asking, well, how much potential energy did it have at the top? So again, that's a nice easy calculation. We'll just go mgh 2000 times 9.8, and the height at the top was what, 30 meters? Whenever you have a potential energy, you do have to say with respect to something. Now they didn't actually do this in this problem, but we're just going to assume that the h is 0 at the lowest point. And that's my recommendation, is that when in doubt, just make your your h equals 0 at the lowest point. So I can tell by the answer that that's what they did. So 588,000 joules is the energy, potential energy at the top. So what's the total energy? Well, the total energy is just going to be the sum, right? So the E total at the top is going to be the KE plus our UG at the top. So you just add those up together. I'm getting 613,000 joules. All right, so the next question's then saying, what is the speed when we reach point B? So how fast are we moving when we reach point B? Well, at point B, notice that we only have kinetic energy. If we define B again as the h equals 0 point, the lowest point, then that means at point B we have only kinetic energy. So if we're solving for the velocity down at the bottom, we'll use E initial equals E final, and this one, we already know the total energy of this system. Once you know that, you can just keep that throughout the problem. So the energy at B is, I really should probably just write kinetic at B, right? The kinetic at point B is 1/2 mv squared. So that would be 1/2, again the mass was 2,000, times v squared. And again, that was equal to the total energy, which we got to be 613,000 joules. Okay, this cancels out to 1,000, right? And that means that this cancels out, which means we have the square root of 613. So I'll let you go ahead and do that out. I'm getting a V of 24.8 meters per second. The next question is now asking, all right, what about at C? So notice we're going up a little ramp here. So at letter C, we're still moving, so we still have kinetic energy, but now some of that kinetic from the bottom is turned into potential energy. So at letter, what letter are we on here? E. So at letter E, we're going to say again, E initial equals E final. Now our E final here is going to be both potential and kinetic energy. And And this is going to be essentially at point C, right? So our initial energy, we just keep that the same, 613 joules. And now we have some potential, mgh, plus some 1/2 mv squared. Okay, let's calculate the potential first. So this potential is going to be 2000 times 9.8 times 10. So I get 196,000 joules of potential energy. So that means whatever's left over is going to be our kinetic, right? That's going to be how much kinetic we have plus the leftovers of kinetic. So if we subtract those two, let's go over here, we're going to have a certain amount of kinetic left over. And that kinetic is 417,000. So when we 1/2 mv square that, I'm going to let you do the algebra at this point. It's good practice anyways. Just confirm that you get what I get. So I get a V of 20.4 meters per second. Alright, let's keep going. So letter G, actually I guess letter F. Letter F, what is the total energy of the system at point C? So this is really just a conceptual question. If you've been following along, you already know the answer. The total energy is, well, the energy that we've been using the whole entire time, right? So the total energy is just simply going to be 613,000. All right, now we're going to stop the roller coaster. So the coaster is moving, right? We have some motion here, and then we're going to stop it. So we're basically slamming on the brakes, and we know it stops in 20 meters. So we're going to have to do some work on it, right? And so that work, that energy is being turned into work done by friction, done by the brakes specifically, but that's going to change into heat, right? If you feel the brakes after that, they're going to be super, super hot. So there's multiple ways to approach this. So again, we're going to do our E initial equals E final. Now you have to be careful here, actually, because if we want to use our E initial of 613 like we've been doing, perfectly fine to do that. But what you have to remember is that number is based on the ground being our h equals 0 point. And when we're at point D, we are still above the ground, right? We're still above that lowest point. So we would say, all right, 613 equals potential energy, because there's still some potential, plus whatever work is being done by friction. Some people actually would put that minus work of friction over on the other side. That's perfectly fine too. I like to think of it in terms of like turning into heat energy. That's what the friction is doing. But both ways are good. So if you want to use that total energy, you can do it this way. You just have to make sure you include that potential there. Now sometimes what I'll like to do actually is just change my reference level. So I'll call the new reference level, let's say this is like C and D here, I'll call this the new h equals 0 point. And that way I only have kinetic energy here because my potential would be 0. And then that's going to directly turn into work of friction. So both ways will work for you. Just for our purposes, I'll do it the way I like, which is kinetic equals work of friction. So in this case, we'll go 1/2 mv squared equals force times distance. And we are going to use the velocity at that point. So the velocity at that point we got to be 20.4. We'll square that out. And then we're looking for force, right? And they told us that it stopped in 20 meters. So anyways, I'll let you do the algebra, do the math on that one, and we get a force of 20,850 newtons. All right, let's move on to question number 3. All right, so this time we have a car. It's going to be accelerated from rest up to 10 meters per second in 3 seconds. So this actually looks like a nice easy question, right? So we have work equals force distance. Oh, that's not going to work, is it? Because they don't give us the force or the distance. Remember that work is also turning into kinetic energy. So we can say E initial equals E final. We're going to say, all right, the work of the car is now turning into kinetic energy. So to find the work, we're actually finding the kinetic energy here, right? And then we know that that energy came from something doing work, in this case, the engine. All right, so when you solve it, you get 75,000 joules. That was letter A. Let's do letter B. Letter B is then how much power. So again, power is the change in energy over time or the work over time. In this case, they're both the same thing, right? So our change in energy went from 0 to 75,000 joules. And that took 3 seconds. So we'll just simply divide that out. We get 25,000 joules per second, or 25,000 watts. All right, that was easy. Let's move on to number 4. So this question, we have a student. They're going to climb up a rope. They have a certain power output that they're capable of doing. And we want to essentially know how long it takes them to climb up. So again, power is change in energy over time or work over time. In this case, we're going from no energy down here, and then when the student's up at the top, they now have potential energy, right? So our change in energy is simply our potential energy. So yeah, so that would be mgh over t equals power. So we got 200, I'm going to write it as joules per second, just a little bit more conceptual. So we're going to go 50 kilograms times 9.8 times, how high did they go? 5 meters over t. All right, do some algebra, and we get 12.3 seconds. That's how long it would take them to go up. Okay, letter B, how much work did they do? Well, that again would just be the potential energy, right? So all the work I do is going to turn into potential energy. Let's just kind of derive this. Okay, we know that conceptually that's what it is, but remember, work is also force times distance. Well, if I want to lift myself up a rope, I basically have to apply a force equal to my weight, right? There's me trying to pull myself down, weight trying to pull myself down. So if I want to pull myself up, I have to lift up with my weight, right? So that would be mg, and then the distance would be the height that I lifted at. So anyways, we'll just go ahead and do that out. So we're going to have 50 times 9.8 times 5. And we get work of 2,450 joules. All right, let's move on to the next one. All right, so in this one, we are dragging a suitcase across the floor at an angle, right? So we're going to be calculating work and power again. But remember, work is force parallel to distance. So you can't simply multiply 40 times 263. We need that force that's parallel. So in other words, part of our force is horizontal and part of that force is vertical. Now the one we care about is that horizontal force, because that's the one that's parallel to the distance that we're traveling here. So according to our triangle, that would be 40 newtons times the cosine of the angle. And then we'll multiply that by the distance. So 263 meters. That gets me 6,477 joules. So that's how much work I do. Okay, and we're going to do that for 1 minute, and we want to find the power. So again, power is work over time. So we just calculated the work, 477, and they said 1 minute. Don't forget, you do have to convert that to seconds. So we're going to divide by 60 seconds, and I get 108 watts. I don't know, the answer says 104, so I don't know. Probably some rounding issues somewhere, but 108, that's what I'm getting right now, so I'm going to go with it. Alright, let's do the next one. Alright, so we have a base runner. They're going to slide into the base and stop. Okay, and so we're looking for more work again. So for this one, so the runner has some kinetic energy, right? They're moving before they slide. And then at the end, they have no energy. Well, where did that energy go? It turned into work. Okay, friction, specifically, you know, some heat energy. Okay, they might get some burns, for example. So they're asking for the work. Well, if we're looking for work, we can just find their kinetic, right? Kinetic is turning into work. So we'll say 1/2 mv squared equals the work. So 1/2, 70, how fast were they moving? 4 meters per second, 4 squared equals work. So that gets us 560 joules of work. So the next question is, well, how far does he slide? So notice that once he's on the ground, right, there's friction opposing him. So the work is being done by the force of friction. Okay, so the work would be the force of friction times the distance. We'll recall the force of friction is mu times the normal force. And if we're on a nice flat surface, then the normal force is going to be the same as mg, or the weight. So the work was 560. Mu was given. This was the coefficient, basically how rough the surface is. The mass of the runner was 70, and little g is little g. Solve for the distance, and I'm getting 1.17 meters. Alright, let's move on to the next one. Alright, up next we have a gorgeous looking problem where we have a Tarzan swinging from a vine. He's going to kind of swing from a vine like this, and then he's going to like jump, let go, and fall into some water. And you're basically trying to figure out, where does he land, right? So where does Tarzan land? So the first thing we have to do in this type of problem really is to figure out, okay, how high is he from this lowest point? So if we call this point right here, like our h equals 0, we want to find out how high he is above that point. So what is this h going from here up to the starting point? So recall this. The vine is 30 meters, right? So 30 meters when he's here at this point, but it's also 30 meters down here. The vine's length's not going to change. So he's also 30 meters right here. So that means if I kind of like cut this across right here, I can make myself a little triangle here, right? And so if you look at this right triangle right here, we can solve for this distance right here pretty easily, right? So that's adjacent to the angle. So that would be 30 cosine of 37. So 30 cosine 37 gives me 23.9. So that's this distance. So that means the height, if this down here is the whole thing is 30, that means the height should be the difference between those two, right? So that means my h in here is going to be 30 minus basically 24, 23.9, so that's going to give me 6.1. So that's kind of my starting height. And we need that because, well, he starts with potential energy, and then right here, he has kinetic energy. Okay, so when we do our calculation then, this is just going to be a pretty basic UG equals KE. So we start with some MGH of that height we just calculated, and that's going to turn into kinetic energy. So this one we can cancel the masses. I guess I didn't even give the masses. It's kind of a hint. If they don't give you the masses, you can probably assume that they're going to cancel out. So I'm going to use that height of 6.1 equals 1/2 v squared, multiply both sides by 2, and then square root it. So I get 2 times 9.8 times 6.1, and then we'll go ahead and square root that guy. And I'm getting 10.9. I guess I could have just looked at the answer, but I just want to verify. So 10.9. All right. So letter B saying, well, what if he's not starting from rest? What if he's starting with a velocity? So in other words, the initial energy is not only UG, but it's KE plus UG. So in that case, we're just gonna include that kinetic energy component. So there's a little bit more starting energy, right? So we'll go 1/2 times 4 squared. Again, we'll cancel the masses there. 9.8, 6.1 equals 1/2 v squared. This time I'm just going to trust that the answer is right. Go ahead and verify. You can let me know in the comments if it's wrong, but that's going to be 11.6 meters per second. Makes sense to me. It's moving a little bit faster, not a ton, but a little bit faster there. One thing you can't do, I just want to point this out, because some students will do that. They'll say, oh, it's 10.9 here, and they'll say plus 4 meters per second. Means it should be like 14.9. No, it's not that easy. Remember, kind of these v squared components, that's going to kind of screw up that nice little linear math there. All right, letter C. Letter C is just kind of a review problem, not in this unit, but it makes the problem a little bit more fun, right? So we're going to have him jumping off this cliff, and basically this is a two-dimensional kinematics problem, right? So at this point, it says use that speed we just got. It's 11.6 meters per second, and then we're going to try to find out how far he lands from the base of the cliff. So the height of the cliff, they said, was 20 meters. All right, so just recall, we're just going to kind of break down our variables, right, into two components, x and y. So we have our v initial in the x direction is 11.6. In the y direction it's 0. It's going to assume it's perfectly horizontal. He lets go at the bottom of the ramp, or bottom of the vine. V final is unknown. Actually, it's 11.6 for x, because remember, the acceleration is going to be 0. But in y direction, we don't know that. We do know the y acceleration is just gravity, right? Negative 9.8. And the displacement in x is what we're looking for, and the displacement in y is negative 20 because they're falling. And then we're going to look for time, right? Well, we're actually looking for dx, but we're going to have to find time first. So let's do the y direction first. So we'll go dy equals VOT plus 1/2 AT squared. So this would be negative 20. Remember, the initial was going to be 0 because it's all horizontal. And we'll go ahead and find the time. So let's see. 20 times 2 divided by 9.8 gets us 4.08, and then we'll go ahead and square root that. Looks like it's about 2 seconds or so. 2.02 seconds is what I get. So that's the time, But remember, the time is the same in the x direction as in the y direction. So we'll just do the same thing now. We'll look for delta d in the x direction. So we'll use that same equation. Notice that the acceleration is 0 in the x direction, okay? No air resistance. So there's nothing like speeding it up or slowing it down in that direction. V initial is going to be 11.6, and then the time we just said was about 2. So it looks like it's about, what, 23? And according to my key, it says it's 23.4. That looks right. So that's where he would land, 23.4 meters. All right, let's move on to the next one. All right, wow, I did not know what happened with the formatting on this. Sorry about that. So we have a skier. They are going up, being pulled up a hill, okay, by like a cable here. Okay, this is 35 degrees. Okay, the speed v is 2 meters per second, and we want to know what's the power. So remember, power is work over time, okay, which is force times distance over time. Now I do want you to notice here that if we group distance over time together, we actually get force times velocity. So that's another way that we can solve this problem, is just by finding the force, since they gave us a velocity, and that will give us the power. So we are on an inclined plane, so they do say it's frictionless. If not, I know it is because it's a skier. Whenever there's the skiing problems, they do that so that it's frictionless. So anyways, that means the only thing that's kind of opposing is this component of gravity coming down the hill. So if you recall, we have gravity, like pure gravity is going to be mg this way, right? But then part of gravity is pushing into it and part of gravity is pulling down. So hopefully by now you kind of know how to find those two. So the one that's going into it is going to be mg cosine theta, and the one that's trying to pull us down is going to be mg sine theta. If you don't know those, I'll link to a video on inclined planes, or just Google inclined planes. I've made plenty of those. So the force then, that means that if gravity is trying to pull me down with that force, then I have to pull up with that same force if I want it to be at a constant velocity. So the force then should be mg sine theta. That's the force going up, and then we'll just multiply that by the velocity. So our skier's mass was 70 times 9.8 times sine of 35 times 2 meters per second. All right, I'm guessing that 800 is rounded, so I'm just going to go ahead and plug it in and see what I get. So 70 times 9.8 sine 35 times 2 equals 787. So if we go to 3 digits, that's going to give us 787. Again, that's watts or joules per second for our power. All right, let's move on to question number 9. All right, let's go ahead and draw this one out. So basically we have a block and a spring right here. We're going to compress the spring 10 centimeters this way. Okay, then we're going to release it. So when we release it, obviously it's going to start moving, right? Okay, and then it's going to hit some friction and eventually stop. All right, and we're just going to be solving some things along the way. So the first thing we're looking for is how fast is it moving after traveling 5 centimeters? Ooh, that's a bit tricky. So notice they're not asking like how fast is it moving when it releases. They're asking how fast is it moving when it's right here in the middle. Okay, so just kind of visualize what's happening. The spring's going back. We're going to release it, and it's going to start moving. Now at this middle point, the spring's still pushing on it, right? So in other words, if we do our E initial equals E final, when we push it back, it has 100% spring potential, like way back here at the 10 centimeter mark. But when we're at the 5 centimeter mark, yes, it has some kinetic energy, but the spring is still compressed. So it has spring potential or elastic potential as well. So at that point, it has both types of energy. So that's how you want to approach this. So we'll go 1/2 mv squared. Oops, no we won't. We'll go 1/2 kx squared. 1/2 kx squared equals 1/2 mv squared plus 1/2 kx squared. And remember, the x's are different, right? So for example, this x, what was our k? 105. This x was 10 centimeters. Don't forget to convert, so 0.1. And then this x, I'm going to flip these if you don't mind. So this would be 105 times 1/2. This x would be 5 centimeters, so we'll put 0.05 squared. That's going to be plus the 1/2 mv squared. Okay, so let's do that out. Let's just go ahead and pull this up a little bit. So the first term we get 0.525 joules. The second term, so we still have some potential energy, we get 131 joules of potential energy. Now whatever's left over is basically that kinetic energy, right? Whatever's left over there. So when you subtract those, 0.525 minus 0.131, you get 394 of kinetic. Okay, 1/2 mv squared. What was the mass, by the way? The mass was 2. Okay, so that's nice. 2 cancels. So we'll just go ahead and square root that number. And I get, hopefully what my key says, 0.628. 628 meters per second. Okay, so be careful on those. Some students, they really want to just say, you know, all or nothing, potential or kinetic. But in that case, in this case, it's actually both at that point. Now letter B, on the other hand, this is now looking for the max velocity. So the max velocity would be when all that potential energy gets turned into kinetic energy, right? So in this case, we actually already know that potential energy. That was right here, right, when it's fully compressed. So that would be 0.525 joules of potential. And that's now how much kinetic we have. So when we square root 0.525, 0.525 square root equals 0.725. 725 meters per second. All right, so now we're hitting that friction. So we're now going to hit that friction, right? And it's going to come to rest. So once again, we'll just use E initial equals E final. And at this point, again, I mean, you have your choice, really, to be honest. You could use your spring potential way back at the beginning. You could use your kinetic total, not the one in the middle, but the total. But all we know is that all that's going to get turned into work of friction. All right, so I'm just going to use that number that we already calculated. So 0.525 joules equals, well, work is force times distance. This is friction, so friction is mu times normal. And since we're on a nice flat surface, that's mu mg times d. Okay, so our mu is what we're calculating, right? So this was 2, this is 9.8, and it says it traveled 25 centimeters, or 0.25 meters. Okay, calculate out mu, and I'm getting 0.107. All right, let's move on to the last review question. All right, here we go, last question. So we have a little spring here. We're going to put a mass on it. We're going to push it down 10 centimeters, or 0.1 meters. And then we're going to let it go. Boom, the thing's going to fly up, 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 up. And it's going to go, we don't know how high it's going to go. We're looking for this height above the lowest point. So if we call this h equals 0, we're looking how high is it above that point. So once again, we'll go E initial equals E final. And we'll go ahead and release it, right? So that means when we push it down, we're going to call this our bottom, our reference level here. When we push it down, we have only spring potential. And then since this is our bottom point, when it's way up here and stops, then that means it has only gravitational potential. So we're just going to go 1/2 kx squared equals mgh, and we'll go ahead and solve it. So 1/2 times 5,000 times 0.1, since it was 10 centimeters, times the mass of 0.25 times little g, and then we'll solve for h. Alright, so I get an h of 10.2. I think that was too easy. Let's add a bonus question. So the bonus question is, what is the velocity right here? The velocity at release. How fast is it moving there? Alright, so again we'll do our E initial equals E final. Now the temptation here, and what will trip some students up, is they'll want to say, okay, it's US is the starting point, and then that turns into kinetic. But remember, there is gravitational potential as well. At this point of release, if we're calling the bottom like our h equals 0 point, right, then there is also UG right here. So we have to include that as a part of our calculation. Now, to be honest, in this case, it's probably not going to have much effect, but you know, there will be times when it does. So let's just do it right. And you know, honestly, a lot of times you'll see this, they'll just ask you to solve it with variables. And heck, why don't we just do that too? Why don't we solve it with just variables? Actually, that algebra is going to look messy here. We'll do both. So that means we're looking for height, right? No, we're looking for velocity. So we'd go 1/2 kx squared. Now notice that this h is actually the same as x. So this would be minus, let's just go ahead and subtract it, okay? Minus mgx equals 1/2 mv squared. Okay, so I said we do it with variables, so let's go ahead and do it with variables. Multiply both sides by 2, so that's going to cancel out the half, so you'll get kx squared, and then we'll go minus 2 mgx, and then we'll go ahead and divide by the m. Divided by m, that equals v squared, and so if we square root both sides, we'll get that. So if they asked us to solve with just variables, there's that beauty right there. Let's go ahead and plug in the numbers and see what we get. So what was k? K was 5,000 times 0.1 squared minus 2 times 9.8 times, oops, I forgot the mass, 0.25 times x 0.1 divided by the mass, right? 0.25. And then square root all of that. So there's that beauty. I'm going to go ahead and do that and see what I get. So I get a velocity of 14.14. All right. So that brings us to the conclusion of these. Hope that was helpful. Let me know in the comments below if you have any questions or if doing something like this is useful, and I'll try to do more. All right. Have a great day.